Very good. Okay, so I wanted to mention two things before we get started with the new work. One was to hopefully just close out the Lie group theory work, and then a brief review of the time evolution that we talked about last time, and then to continue. And I felt like, so Doran asked a question, which I'll come to in just a second. I had a sort of an idea of how to visualize in a potentially useful way. So if this is useful, great. If it's not, forget it. What we're trying to do in terms of constructing the possibly projective representations of our symmetry transformation Lie group in quantum mechanics, excuse me. So what we want is we want a map and a vector space, which are connecting the Lie group of interest and the set of linear invertible maps. So we seek this pi hat. But let's just say we know that if this group G is topologically non-trivial, and very, very tangentially, not tangentially, but like in a way that we've not discussed in class, if the algebra is non-trivial in a similar way, if there are central extensions, I'm just using that word, don't worry about it. But if the group has topologically non-trivial properties, like it is specifically if it is not simply connected, then our procedure is to go to the universal cover of the group, this G twiddle, and we seek the representations pi twiddle of this universal cover, which are going again to the set of invertible maps. So I'm trying to draw one line here in this direction, and then in the same plane as this line is a line out here. And then I'm going up into the third dimension by saying, look, we want this, this representation from the universal cover to the general linear group. And instead, what we do is we go up to the Lie algebra of the group of the universal cover, which is the same Lie algebra as the group. I didn't write that. I mean, maybe I could actually add that too. So there's a similar exponential map here. Apologies if that makes it more complicated. I am trying to make it simpler. So I'm going up into say the third dimension here of maps for the Lie algebra using the exponential map. I'm finding the representation of the Lie algebra on the set of the Lie algebra of the set of linear invertible maps, and then coming down by the exponential map into the set of linear invertible maps, which once I've chosen a basis are matrices, and matrices we like. We know how to do matrix multiplication. We know how to find eigenvalues, eigenvectors, so on and so forth. And so in our quest to find this map and this vector space, we go to the universal cover, we go up to the Lie algebra, we go over to representations of the tangent space of the set of linear invertible groups, and we go down to here, which gives us the vector space. And then because of this whole set of mappings, it gives us the map that we seek. Yes?
Two questions. What is A?
A is in fact, so I'll give you the correct technical explanation, which is not something I would necessarily expect you I would not expect you to know it for the class, but I think it's a nice thing to know. This A is what's known as the fundamental group. So this is an extraordinarily powerful tool from algebraic topology, and it gives you a way of characterizing, one of ways of characterizing shapes. So it's about basically how many times you can wind around your manifold in a closed path, such that it's not contractible to a point. So as an example, any space that's simply connected, the fundamental group is trivial. It's just the identity. If you have the circle, it's the integers, because you can go around an integer number of times clockwise or an integer number of times counterclockwise. SO3, the fundamental group is Z2, the group of two elements, 0 and 1, because you can have a closed path that goes around once fully that is not contractible, or it can go around within the group and it is contractible. And going around twice is equivalent to just going around within. So that's why it's this pi2, the Z2. And I put this on here because this is a short, what's known mathematically as a short exact sequence. Again, something that I wouldn't expect you to understand on a deep level in this course, something I just want to expose you to the words of. And because really crucially and in a beautiful way, in which so I have the first problem on the homework set, which is, I would say, it is truly exceedingly optional. It is, I would say, not fair to expect you to address that deeply in this course. But I would hope that you just read it and maybe read some of the stuff and get some of the ideas. And one of the important things, so valuable, you know that these representations here from our group are representations up to a phase. And a valuable question is, what values can those phases possibly take? And you should know from undergraduate quantum mechanics that for the group SO3, your representations are up to a minus sign, that rotating a half integer representation by 360 degrees gives you a -1. And you showed that explicitly, I think, in the last homework. You could ask, well, can I get any other phases for SO3? Could I get an e to the I pi over 4? Or could I get I don't know, any other thing? And the answer is absolutely not, because the possible phases you can get are restricted completely by the fundamental group. So the fact that the fundamental group of SO3 is Z2 tells you have two possible phases, the identity and -1. In just a second. And then for SO2, the fundamental group of SO2 is the integers. And as we talked about, I believe in the last class, the set of phases that are possible for the integers are, you have discrete steps that go from -infinity to +infinity and steps of +1, multiplied by whatever the particular representation is.
Oh, no, I was just going to say, I think that.
Okay. Yeah, super.
Other question, sorry.
Was this a follow-up on?
No.
Okay. Okay, sure.
Why do we need to go up to the universal power level if the group is not connected? What makes it difficult to power it?
I don't know that this is going to exactly answer your question, but we know from the math that all of the representations of the group of interest are in a one-to-one correspondence with the representations of the universal cover, where some of the representations of the group might end up being projective. All the representations of the universal cover are ordinary representations, and which is in some sense they're easy. And then, especially if the universal cover is a compact Lie group, then we have the theorem of highest weight, which gives us an algorithmic way of constructing all of the representations of the universal cover. Yeah, you're welcome. Rachel, and then on. Unless this is a follow-up? Okay, great.
I was going to ask the pi tilde.
Yes, this one.
Where is it going from?
It's going from the universal cover.
Okay.
Yes. Exactly, yeah. So maybe I can try to, like so. Yes. So in practice, yes. So in practice, you could go to the Lie algebra and you figure out this pi twiddle hat prime and so on and so forth. But this is what you're actually doing. And that it's these several powerful mathematical theorems that I've been referring to that you're really in previous courses you've been implicitly relying on. And I wanted to expose you to what the deep mathematical machinery is. Yeah, because I think a fundamental question coming back to Doron's question from last time is, I think it's clear, but let me just say again, what we're as physicists deeply, deeply interested in is the complete classification of all possible unitary irreducible representations of the symmetry group of interest. Because that tells us all the possible particles that can live in whatever physical setup that we have, and how to manipulate those particles under symmetry transformations. So there is this tried and true method in mathematics of guess and find out. So you could guess a bunch of you could guess some representations and see if they're unitary and irreducible. And not casting aspersions on your suggestion, but doing what you suggest in my book would be that guess and check method. But what you're suggesting without relying on the deep mathematical machinery in no way guarantees that you've completely classified and completely found all of the unitary irreducible representations that you're interested in finding. So for example, right, if you are like me and sort of naively try to find the unitary irreducible representations of the rotation group in 2 dimensions, you're like, cool, it's just a phase, e to the I n phi, and I require n to be integer because I require there's a continuity of my wave function going around the circle. That's all well and good, but you would be, I would be incorrect. Like there are in fact particles or quasi-particles that have behavior that's not described by those sets of representations. And there's a deep and important mathematical reason why that is true. Just a second. So as I segued into this, I believe your question from last time was, why is it, let me try to paraphrase it. Why is it that in SO3, the representations are classified by a discrete number, and in SO2, they're classified by a continuous number? And I can definitively answer for SO3. SO3 is a compact Lie group, and the full classification of compact Lie groups is completely understood, and it's dictated by the theorem of highest weight. And my understanding of a relatively decent dive into mathematics since then is that the classification for what are known as non-compact semi-simple Lie groups, of which say the translations are 1, is to this day not fully understood mathematically. And I updated the comments of the video. I believe I did this, you can just double check, of that video with a link to a relevant stack exchange that discusses this in some more detail. I don't want to say much more because I really don't understand. I get the vague sense that it's mostly understood, and I'm kind of guessing it's sort of edge cases, but I don't really have a full understanding. Yeah, great. I think you've been waiting very patiently. Or did you already ask? Okay, great.
So the representation of
yeah. So this map.
We get extra representation that didn't come from like SO3 doesn't ask me.
So SO3 does not have ordinary representations that are half integer. Yes.
But is this how can you write down representation that one?
I'm sorry, can I write down A?
Representation.
Oh, absolutely. Yeah. I mean, that's the one that you know and love. The sort of 2D complex vector space, Pauli matrices for the generators. That is absolutely the projective representation for SO3, or what we would call in physics spin 1/2. It is an ordinary representation in SU2, yes. Yeah. And what happens is, in a way that, I mean, maybe I could try to make an optional problem on this, but, you know, if you go around in so SU2 is just physically bigger than SO3. So in SU2, in sort of somewhat in air quotes, you going around in a full circle is not 360 degrees, it's actually 720.
And logically you can do that.
Yeah, you basically go around twice in a non-trivial way in SO3 to get that 720. But in SU2 in a way that's I cannot visualize because it's a three-dimensional sphere, which is in 4 dimensions. But if you think about like a 2D sphere, and you think about like going around that, like whenever you go around a 2D sphere, you can always sort of slip that path to a point. And that's how I would visualize what's happening with a three-dimensional sphere. You're welcome. Cool. Yeah. So if I take my standard beach ball and I think about some path that's on this, then I can just contract it. And now it's a point, all on the surface of the sphere. And I contrast that with, say, the donut, where if I think about a curve that goes around like this, so I can continuously transform this curve in all sorts of interesting ways, weird and wonderful ways. I'm trying to, maybe I should try to do dashes. I would never be able to get it to a point, you know. I can move it around in all sorts of ways, but I'm fundamentally stuck with always having to be around that handle. Correct. Good. Well, it's a very important concept, and I'm glad that you got it. These are not, as I said, these are not easy concepts, but I think they're really deep and beautiful and of fundamental importance. I want you to have a good appreciation for why electrons exist. That it's this very weirdo quirk of quantum mechanics that allows electrons to exist, and a weirdo quirk of the topological non-triviality of rotations, where you would just think, like, I'm back to where I started, right, folks? And the answer is no, you actually aren't. And that's really weird, but also super cool. And I just love, like, I don't know if you are, so this is a little, let's geek out a bit. But you're at your little like dinner parties, or you're at your like, you know, birthday parties, your bride, drinking your beer, talking with your friends, you're like doing useful things for the world, like saving lives or like writing legislation. And you go, how many degrees do I have to turn to get back where I started in a rotation? And they're like, obviously 360. And you're like, oh, really? Am I back to where I started? And then they're like, oh, that's weird. And you're like, what's weirder? Oh, dang. I'm back to where I started. I went around 720. And they're like, you didn't go around. Oh, really? Let me show you with water, right? I go around 360 and I go around again. And at no point did I spill a drop. I went around 720. And it takes them a while to like stare at it and see it and figure it out. But it's super cool. And then you could say this, and you just say, this is why electrons exist. Like at a fundamental level, that weirdness is what allows us to exist. Okay, cool. I feel like you gained some of the like nerdy appreciation of this that I have, so thank you. Last questions on any of this? All right, super. Okay, time evolution. All right, so we're talking about the fourth postulate of quantum mechanics, which is I partial t on my state ket, which can explicitly depend on time, is equal to my Hamiltonian, which may have some explicit time dependence acting on the state ket again. For many, many reasons, we find it valuable to define the time evolution operator. The time evolution operator takes us from a state at initial time to a state at final time. We talked about the group theory of time evolution. This is a symmetry transformation that is continuously connected to the identity. So therefore it is, by Wigner's theorem, unitary and linear. It has to be unitary and linear operator. Because in quantum mechanics, probability is Conserved. Yeah, yeah. Good. All right. So what does that mean? It means that the Hermitian conjugate of this operator is equal to its inverse. We also have that time evolution from initial time to the same time is the identity. Time evolution from initial time to an intermediate time to a final time is the same as a single time evolution from initial time to final time. And if I think about the inverse of time evolution from T1 to T2, you get the time evolution from T2 to T1, if only it was that easy in real life. Okay, we talked about the infinitesimal expansion of the time evolution operator. Just as a comment from something I saw yesterday at the tutorial, I know when I was a student, I wanted to prove things to all orders. That is the correct lab. If the problem says show it infinitesimally, do yourself a huge favor and do it infinitesimally, because it's easier, and also because we have calculus, we can always exponentiate. So certainly within a local neighborhood, you are always in Lie groups guaranteed that you can exponentiate. And if it's true at infinitesimal order, it's true at all orders within some neighborhood. All right, good. Now things can get, so we have this time evolution operator, and the claim that we make is that if the Hamiltonian is time independent, then we get an exponential. In fact, it's not a claim. You can see it directly in terms of this, this product that looks like an exponential. If a Hamiltonian depends on time, but is commutator, does not depend on time, and is zero, then it's the integral over time exponential, exponentiated words. You see the formula. And then crucially, if the Hamiltonian depends on time, but does not commute with itself at different times, then one gets a time-ordered exponential. Now, I gave you a homework problem where I gave you 3 different examples where spoiler alert, the first one is the Hamiltonian is time independent. The second one, the Hamiltonian is time dependent but commutes with itself. The third problem is that the Hamiltonian is time dependent but does not commute with itself. And cutting you potentially off the pass and saying, boy, that seemed very artificial. Maybe it didn't. But if you thought that, there is a really important reason why I'm bringing up this time-ordered exponential, because this is everywhere in field theory. Because in field theory, then because space and time are on equal footing, you care very deeply about the time. All of your operators depend on time in a trivial way. So for those who go on into field theory, this is the object you're going to be dealing with all the time. And then also, as given in the example, what? Thank you. Yeah, thank you. But there are examples even in non-relativistic quantum mechanics where this is important to understand. Good. Great. All right. Good. So the time-ordered exponential, one could expand the exponential and then enforce the time ordering, where time ordering tells you what order to put the operators in. It's often easier simply to write down what's known as the Dyson series for Freeman-Dyson for this time-ordered exponential, where one is explicitly enforcing the ordering of the Hamiltonians by the choice of the upper bounds of integration limits. I'm going to make a note to myself because there's going to be an important, it'll be a nice question for you to work on. Okay, great. Very good. Now, just to be clear, in what we've done so far, purely on the group theory level, we have written the H as the operator, which is the generator of time translations in the symmetry group. It is the operator that eats the operatorness of the infinitesimal expansion of the time evolution operator at leading order. I have certainly written it as H intentionally as a lead you in the direction of thinking what this should be, which is the Hamiltonian. You see that explicitly through the fourth postulate of quantum mechanics, where the theory of differential equations tells you that if you have such a linear partial differential equation, that the solution, or sorry, so the equation for the time evolution operator, which is I partial t u equals HTU, that you have three possible solutions to that, depending on whether H depends on time, and if it depends on time, whether it commutes with itself. And those three solutions are the exponential integrating over time, and the time-ordered exponential. And that allows one, therefore, to identify this operator here, which we call the Hamiltonian, with this operator here, which is the generator of time translations. Good. I feel like that was clear and brilliantly delivered. Nevertheless, are there any questions?
We agree.
All right, great. So let's continue. Let us continue. All right. Let's talk about explicit time evolution of states. And what's known as the propagator. All right, so let's assume for simplicity that our Hamiltonian is time independent. All right. Then we have that our state at time t is e to the minus I t minus t0 Hamiltonian psi t0. Okay. So how do we proceed? So we know that the Hamiltonian is Hermitian. We know it's Hermitian because, how would you say you know that the Hamiltonian is Hermitian? I'm sorry? I just didn't hear what you said. You're on a right track, right? We definitely are going to demand that anything that we can observe, the eigenvalues have to be real. So can we observe energy? No? Well, this is something that sort of drives to a really interesting point of this course, and what's really deeply satisfying. So I constructed, when I originally came here in 2010, Honors Quantum Mechanics 1 and 2 was a single course. And I thought, what's sort of the crowning achievement that I want people to get to in this class? And my thought process was that in undergraduate quantum mechanics, you see explicitly that the stationary states of the hydrogen atom have certain energy differences, certain energy levels that exactly correspond with what is observed as the energy levels. But how do you observe those energy levels? Because in non-relativistic quantum mechanics, if you only have the central potential of the proton, those are stationary states. If you're in an excited state, you will be in an excited state for all time. What one actually observes are the frequencies of photons that emerge as the hydrogen atom de-excites. And so my goal was, and Mwanda continues, follows in a similar trajectory, to get to the point of introducing a quantization of the electromagnetic field and coupling that to the hydrogen atom, such that excited hydrogen states can de-excite through the emission of photons. So your question is like, how do we observe energy? In the context of the standard model, i.e. without gravity, we never actually observe energy. We only observe energy differences. So that's a fair statement. So I would say, I mean, maybe Tion, so maybe is there another argument for why this Hamiltonian is necessarily Hermitian?
I just thought because.
Okay. I would say we know that we have time translation symmetry. It's a continuous symmetry. So it's going to be represented by a unitary operator. And the generator of those time translations necessarily is Hermitian, because time translation is a unitary operator. And then I would say, for exactly the reasons you state, because the Hamiltonian is Hermitian, it is a potentially admissible quantity to measure, or the eigenvalues can potentially be measured. Candidate. That's a great word. I think I took it from Weinberg. So thank you for trying to credit me, but yeah. Okay, good. So we know that the Hamiltonian is Hermitian. Good. So that means that the eigenvalues are real. What else does it tell us immediately? Exactly. Its eigenkets are an are a complete basis which we can make orthonormal by the Greenwich procedure. So, and therefore there exists a complete orthonormal basis, CON, complete orthonormal basis. Good. Complete orthonormal basis. Say 1 is the sum over n of the outer product of ENs, where the Hamiltonian on EN is EN. So, and okay. Let's see. So now I have a 1. One of the very few things that we can do is insert 1s and insert them judiciously. Why do I want to insert a 1 judiciously? I don't like operators. I do like numbers. So I can get rid of the operatorness by inserting this 1 to turn this operator into a number. So therefore, psi of t is e to the minus I t minus t0 Hamiltonian sum over n en psi t0. So this is sum over n e to the minus I t minus t0 en, and then so en psi t0, and then en. This is some complex number. This is some complex number. So generally, one is given by experiment the initial state, psi t0, and therefore the initial coefficients Cn of t0, which are the overlap of En with psi of t0. And then the coefficients as a function of time, which are the overlap of psi at time t. These are simply e to the minus I t minus t0 En, Cn, T0. So that's very nice. Any questions on that? Yes.
Just when we.
Yes. So if one is in bound states, then this will be discrete. If one is unbound, then it's continuous. One might have some combination of bound and unbound states. Yes. Other questions? Great. Okay. Another common one is if we have wave functions. So we might be interested in the position of a particle as a function of time. Yeah, good. So alternatively, we may insert a 1 that tells us 1 which is defined as the integral of dx of the outer product of x. So then our wave function as a function of time, so that's the inner product of x with psi of t. So this is x and then e to the minus I t minus t0 Hamiltonian psi of t0. And now we can insert our 1. And this object here on the right, this is our psi of x prime t0. Let's name, because it comes around very frequently. So this is the matrix element of the time evolution operator. In the position basis. And it's called the propagator. And we denote it by a K, the final position and final time, and then the initial position and the initial time. I guess let me call this X0, just for notational consistency. Why do you think it's called the propagator? Sorry? Yeah, Raf?
Yes.
Yes. Oh my God. All right. I'll pay you off for that later. Yeah, so we're propagating from the initial time to the final time, integrating over the possible initial positions, and we will exactly show precisely what Raf said, that this is a Green's function, or it's very closely related to Green's function. What one needs to do is one needs to put in a theta function, a Heaviside step function, ensuring that t is greater than t0, and then you get the correct delta function out. But we'll get there, or not. We'll find out. But yes, Green's function, very good. All right. Now, it's certainly described in Griffiths, and I would like to think that you did it at some point in your life where you were presented with the time-dependent Schrödinger equation, or maybe even the time-dependent Schrödinger wave equation. Which was this I partial t, I guess, psi of x and t is equal to this Hamiltonian, which is in terms of, say, x and then minus I partial x and t, and then psi of x and t. Well, actually, let's write it this way. I'm doing this a little bit on the fly. Forgive me the minus sign if I got the minus sign wrong. And then what you do is in Griffiths, you assume a separable solution. That the solution has a part that's only a function of time and only a function of space. And then you get your usual Sturm-Liouville problem for the psi of x, the minus 1/2m partial squared plus v of x. And then the time is just a phase e to the minus I e t. So that is an approach, and it works when the Hamiltonian is explicitly time independent. Just a second. This propagator approach is more general and will allow us to connect not only to Green's function theory, but also to the path integral, which I hope to introduce you to at some point in the future. Yes. Oh, that's a very messy X. I'm sorry. Good. Welcome. Other questions? Awesome. Okay. So let's do an example. And so let me just put this in. So propagator is more general. Will allow for connection to the path integral and for potentials that depend explicitly on time. Okay. So example, 1D free particle. Take T0 equals 0. When I was a student, I hated when professors took T0 equals 0. I was like, oh, you know, T0, it's in there. But I've come to appreciate the symmetry argument that if I have something that's time independent, it doesn't matter what the initial time is exactly. So let's make lives easy, our lives easier. Life is hard enough as it is. And let's take T0 equals 0. So then psi of t is going to be equal to e to the minus I t Hamiltonian psi of 0. And we can go further. This Hamiltonian is p squared over 2m. Let's just stay, we said we're in 1D. Psi of 0. How might you propose that I proceed? Taylor, okay, that's an idea. So if time is infinitesimal, that would be something to do. Let me give you sort of the hint in terms of what I'm seeing, which is I'm seeing an operator and I don't like operators. So I want to get rid of the operator. So what can I do?
There's a bracket.
Very good. I want to insert a 1. What's the 1 that I'm going to insert? Momentum. Ah, perfect. Thank you. Great. So I'm going to insert a 1, which is an integral outer product of momentum. By definition, these are eigenstates of the momentum operator. And so I'm going to get integral dp e to the minus I t p squared over 2m. And then the inner product of p with psi of 0. And then the p ket. I really sort of struggle with how what's the nicer way to write this? So this is nicer to me because it emphasizes the outer product. This is nicer to me because it emphasizes the just pure complex numberness that's happening here. But I visually don't like the wrangle and then the vertical. But okay, this is a me problem. All right. Now it's, I would say, usually not the case that one is given the initial wave state or initial state in terms of the momentum eigenbasis. You're usually told what the initial state is in the position basis. So if the initial conditions are given by a psi of x and t equals 0, what would you propose that we do now? Perfect, yes. Very few things we can do. Multiplying by 1 is one of them. The trick is to figure out which one, and I'm not being facetious. All right, so therefore this psi of t, this is an integral dp e to the minus I t p squared over 2m, momentum operator, outer product of x, and I've got an integral over x over the left-hand side, which I've neglected just because I forgot it. And then I've got my psi of 0. Perfect. Now, we know what the overlap of P with X is. This is 1 over root 2 pi e to the minus I px. I always forget whether it's plus or minus. I just have to look it up or rederive it. Good. Now, if we're given the initial wave function, we probably want not just the final state, but we probably want the final wave function. So let's actually put primes on here. Say if we're interested in the final wave function, psi of x and t, which is x psi of t, then it's the same result. This is here. Then I've got an integral dx prime dp e to the minus I t p squared over 2m. And then I've got now an xp overlap. And so I'm going to have an over 2 pi, and I have an e to the I p x minus x prime psi of x prime and 0. The point is just that when I hit the x on here, it's the opposite of the x prime. So if the x prime gives me a minus I, then the x will give me a plus I. I get a 1 over root 2 from the first one. I get a 1 over root 2 from the second one. So I get a 1 over 2 pi here. And this 2 pi is really a 2 pi h bar because I've got a dx and a dp here. Okay. Do you see a way in which we can make some further progress here? Yeah, I can integrate the p out. And it's a Gaussian. It's a complex Gaussian, so if you want to rigorously derive the result, you really need to do complex analysis. And then you essentially get the expected result. But that's exactly what you want to do. Yeah, very good. And that gives us, in fact, the propagator. So one may explicitly integrate out P to find the propagator. And so if I have some x e to the minus I t h x prime, this is exactly what I have over here. 1 over 2 pi integral dp e to the minus I t p squared over 2m e to the I p x minus x prime. And when the dust settles, this is m over 2 pi I t to the 1/2 power e to the I m x minus x prime squared over 2t. It seems like you've seen this before. Like this seems very satisfying to you. Yeah. Cool. Yeah. So this is exactly the propagator for the free particle. And this is like I really like this way of deriving it. And then when you derive the path integral, maybe you're given the path integral, it better give you this answer. And it does. Yeah. Super. Good. So we're definitely going to see this again. Questions? Okay. Should I pause a little bit longer? All right, I'll take a sip of water. Yeah.
Psi of x.
So if I heard your question correctly, can I do something like this?
Yeah, making x. Psi.
Oh, psi of x. Presumably, yes. So what are you doing here physically? You're treating x as a parameter and t as an operator. Right? This would be the eigenstate of the t operator. So we are used to the idea of considering x as an operator and t as a parameter. So presumably one should be able to think about it this way. I don't know offhand how to think about it that way. I guess you would need to rejigger your postulates of quantum mechanics such that you would have a postulate of quantum mechanics associated, like the fourth postulate of quantum mechanics would be replaced with, instead of having some time evolution PDE, you'd have a position evolution PDE. So you'd have something probably like I partial x psi of x equals momentum operator psi of, with momentum operator that may depend on position, psi ket is a function of position. I think that's how it would work. I would strongly urge you not to think about it that way and rather take things in a more relativistically invariant way and treat both time and space on equal footing. Now, whether you choose to elevate time to an operator or demote position to a parameter, it's up to you. And when one does quantum field theory in the traditional sense with Feynman diagrams, Peskin and Schroeder, so on and so forth, one is demoting position to a parameter just like time is here. But one could alternatively elevate time to an operator. This is often referred to as zero-dimensional quantum field theory. I shouldn't get into it. It's a one-dimensional function. Anyway, we can talk about that later. I think we're getting a little too far off topic to cover that in detail. But it's a good question. Cool. All right. Other questions? Tion's checking his phone. Bad sign.
I'm Googling one-dimensional function.
All right. Yeah, so there's a statement that quantum mechanics is one-dimensional quantum field theory. Okay, so investigating the time of or I guess let's put it, that's pretty vague. Well, what's the way that I like to say it? Connection between time evolution and statistical mechanics. So this is super cool. And is the source of, conceptually, the source of many Nobel Prizes. And some of the most important understandings of how we see the universe. So doesn't take too much recollection that time evolution in quantum mechanics is given by this time evolution operator, this unitary thing, which is e to the minus I t Hamiltonian, taking t0 for simplicity, and the Hamiltonian, taking the Hamiltonian as time independent, and therefore taking t0 to be 0 for simplicity. All right. Taking h t independent and t0 equals 0 for simplicity. Suppose I consider the analytic continuation of time. Rachel Stokes. So you might say, like, time's obviously not complex. Why am I doing this? Well, why would I do this? I'm going to do it because, for the reason you'll see in a moment, it's very useful to do it. But in general, in physics, whenever you have a real number, it's generally going to be valuable to you to allow it to be complex. Both for, just everything becomes easier. Calculation becomes easier. Huge numbers of tricks open up. So complexifying, and you saw this with the theorem of highest weight, even at the level of algebra, complexifying generally makes things easier. So it's valuable mathematically to abstract away from the reality that we live in. One way to abstract away is to complexify. So take t to be minus I beta, which is minus I 1 over capital T, which we're going to take to be a temperature. Beta is some real number. And consider the trace of UH of T. We'll have the trace of UH of I beta, which is the sum over, for example, energy eigenstates, e to the minus I beta Hamiltonian, En, sorry, minus I. And so then this is the sum over n, e to the minus beta En, sum over n, e to the minus energy over temperature. What do we call this in statistical mechanics? It's a partition function. Yeah. So the trace of the time evolution operator for negative imaginary time is the partition function. Story time. 1999 was well before all of you were born, which makes me sad. It was my senior year of high school, my matric year. It was also the 100th anniversary of the American Physical Society. And it turns out that they had their annual conference, which was a very important one because it was the 100th anniversary in Atlanta, where I was growing up. And so their keynote speaker for a public speech was Stephen Hawking. And this was brief history of time, this is amazing. I'd read brief history of time. I might have read Einstein's book on relativity. It's like a little beautiful little short book that you can give to a non-specialist and they can read quite a bit of it. It's very inspirational. So it's like, I'm going to see Steve Hawking. We're going to see this. So we go to this huge lecture hall and he's talking and he's sort of going through the brief history of time book, like following. And at some point, time becomes complex. And I'm like, wait a minute. And I was very, very confused as a 17-year-old who knew some calculus and that was about it. But now looking back on it, I'm like, yeah, that's exactly what you want to do. You absolutely want to complexify time and use it to compute the partition function. Now that I think about it, he probably was talking about black hole radiation. That's probably where that was headed to for him at the time, which I totally was just over my head. Okay. Good. So this will allow for just extremely fertile connections between condensed matter physics and particle physics. Particle physics, one is interested in the propagator and has an enormous number of tools such as path integrals, Feynman diagrams. Condensed matter physicists are interested in the partition function. And so they're able to whole hog take over all of those techniques from particle physics in terms of path integrals and Feynman diagrams and apply them to the condensed matter setting. Conversely, one has an enormous amount of intuition from the condensed matter setting where you have clear separations of scales. Like you have macroscopic scales, you have microscopic scales, and there's this idea that the microscopic scales cannot influence the macroscopic scales and vice versa. And that comes over whole hog into the particle physics arena in terms of the renormalization groups. That was all Wilson, again, Nobel Prize winning work. And so also, for example, all of Anderson's work on symmetry breaking and superconductivity. That was the Higgs mechanism, and Anderson understood it completely, and Higgs understood nothing. Yeah, Anderson's well appreciated in the field, so he's fine. But this is one reason why this connection is extraordinary. Two, I guess, good reasons why this connection is extremely valuable. So I wanted to introduce that idea to you. Yeah. Yeah, I have asked that question. Like, is there a deep reason for this connection to many people, none of whom have given me a memorable answer, or which is say a satisfactory answer. And I made one last attempt last night, like just Google it yet again. Has anybody posted anything on Stack Exchange? And nothing that I've ever found. So I'm not aware of. My gut instinct says that there must be, that it's not just a mathematical trick, that these absolutely fundamental objects in these two different fields, my gut says it can't be just a coincidence that they're so deeply related. But I don't have a better answer for you than that. Why is the canonical ensemble the trace of the? Okay, so the partition function, I would say, usually is introduced as this object, e to the minus energy over temperature. But this is a basis dependent statement. And so we would rather have something that's more general. So I can just go backwards and say, well, this, we all agree, is equal to this, which is equal to a trace. And now I'm able to change bases. So I could, for example, think about rather the integral dx of xe to the minus beta h x. And that might be an easier quantity to evaluate than the sum over energy eigenstates, for example. Yeah. Good. Was there a question over here?
Sort of like some
So there's the Boltzmann equation, which I think is sort of scattering things. I mean, Boltzmann was a very smart person who made contributions in several areas. So I think the short answer is yes.
maybe some
Can't say. Good. Last questions. Great. All right, let's talk about active versus passive transformations. All right. So let's first introduce the idea. One may think of a symmetry transformation of a system in two equivalent ways. So one, in an active transformation, the system is transformed while the coordinates are left unchanged. And two, in a passive transformation, coordinates are changed while the system is left unchanged. I think it's valuable to draw some pictures to illustrate this. So suppose we have a function f of x. And let's draw this function and let's give it a bit of a shape so it can help us visualize what's going on. So let's say it's sort of a lumpy thing. And now suppose we want to propagate this, like this might be a ocean wave captured at a particular time. And where does this wave go after some amount of time? So there are two options. So suppose we wish to model the propagation of f of x to the right by an amount A, i.e., we're performing a spatial translation. So I would say that probably the obvious thing to do is just remove the function. And apologies if you take umbrage at obvious. I'm open to other suggestions for naive, I don't know, obvious thing to do is to move f of x to a new function, call it f prime of x, which is f of x shifted to the right by A. Sorry, I'm sort of stuck in terms of space here. I'll try to keep it up as much as possible. Why am I doing it this way? I think I literally have a tablet. Let's copy paste. All right, so here's our original function. Now let's shift it to the right. So this is now f prime of x, and this is now x0 plus a. I could probably even do better, and I could actually copy. Why don't I just do that? Again, I've got a tablet. Why am I making things unnecessarily difficult for myself? Good. So the above is an active transformation. And the question is, the question always is, right? So we're describing the system. One could say, yeah, how to describe a system that has been transformed, or which would be the active view, or equivalently, how do two different people in two different coordinate systems describe the same system, which would be the passive view, which we'll get to in a moment. But this is not an academic question. This is very important for us to understand. So, and it's very important to be able to understand how these things are related to each other, because we need to be able to compare predictions. So how are f prime of x and f of x related? Where here, to be pedantic, and it's obvious here, but it will not be obvious in just a second, the coordinates remain the same. So how are f of x and f prime of x and f of x related in an active transformation? And up to signs that I always make mistakes on and I have to think through carefully, the answer is quite easy. Well, ask questions if you disagree. That this f prime of x is equal to f evaluated at a different point. That different point is x minus a. And I always get this sign mixed up. And the point is that I have to sort of look at the peaks. So f of x is peaked at x0. F prime of x is peaked at x0 plus a. So if I plug in for x0 plus a into this f, I have to get x0 back. So it's minus a. Good. All right. Good. Questions? All right, great. Alternatively, we could have captured the propagation of f to the right by a by shifting our coordinate system. To the left, while leaving our function unchanged. So if I come back here, copy, paste, and now what I do is I say, no, just kidding. Whoops, trying to sort of visually judge about the same distance. Now I have some x prime coordinate system where this distance is a. And now this point in the prime coordinate system is x0 plus a, right? It is x0 plus a. And I would like to understand how to describe this new function in the new coordinate system. So how are f prime of x prime and f of x related in a passive transformation? And here, explicitly notice how the coordinates are different. So I have that f. So how are these related? Well, the function hasn't changed, right? It's still the same thing. So that tells me that this f prime of x prime has to be equal to f of x. Good. Yes. I'm sorry, I didn't hear what you asked. No, it's the x. Yeah, it's weird. Yeah. So I think we're used to f of x, right? So I got some coordinate system, I got my function. And now I'm changing my coordinate system. In this case, shifting to the left by a. How is this same function described in a different coordinate system? Possibly a useful connection back to quantum mechanics. I can think about my state as a ket, it's an abstract vector. And I can ask, how does this vector look in various bases? I can ask, what does it look like in the position basis? Straightforward. How does it look in the momentum basis? Oh, it looks totally different, and I'm used to that being totally different because it's now on the momentum basis. Engineers would call this a Fourier transform. But I could just as easily think about, okay, well, how does Doron describe the state, and how do I describe exactly the same state? Doron is a coordinate system because Doron is very selfish and self-involved. His coordinate system is centered on him. I'm very selfish and self-involved. My coordinate system is centered around me. But we have to make the same predictions. And so whatever the state Doron says the state is in, I say is exactly the same state.
Subtract a the next prime.
I I get very uncomfortable with active and passive transformations. I'll be honest with you. Like, I still don't think I have a good intuitive feeling for them. I get very squirrely with them. So if that is a way that makes you feel like that gives you a good intuitive feel, I am not going to be one to disabuse you of that thought. Yeah. Good. Other questions? Great. I probably shouldn't say these things that are being recorded. Some alien in the future is like, God, this guy, what an idiot. Okay. Also being recorded. All right. So let's think about this. So let's see how this works. For translations. So, and actually, let me sort of backtrack in terms of sort of being honest with you about some of these things that I find difficult. I'm hoping that that's a valuable for me to say to you that these things are hard, and I've been doing this for 25 years, and there's still some things that are hard. And so I hope that it doesn't make you feel defeatist, but rather, if you are having difficulties, I would say it's entirely natural. These things are difficult. And office hours are 4 o'clock. All right, great. Good. So let's see how this works for translations. So in this case, I have, say, translation by A acting on X. This gives me X plus A. So then under an active transformation, so I've got f prime of x, we said is equal to f of x minus a. That's what we said up here. So what is that in terms of the transformation? That is f evaluated the inverse transformation on the coordinates. And under a passive transformation, f prime x prime equals f of x, we have f prime of x plus a is equal to f of x. So that tells me that my f prime of the symmetry transformation is equal to the original f. And then this will generalize for any general transformation. So f prime of x will equal, so any general transformation ta of, or rather t of some theta a. This will be f of t inverse of theta acting on x. This is the active transformation. And f prime of t of theta x equals f of x is the passive transformation.
The active line is that minus one?
Yes. So like the inverse that we had here. Yeah. So just to be explicit, I mean, I think you will get it, but in the homework that we were working with yesterday, yeah, Doran's nodding, right? You saw that the rotation operator acting on a function gives you f of the r inverse. So that's the same idea. So the next part will be to talk about active versus passive transformations in quantum mechanics, unless there are questions here. pause. Sip. Last call for questions on the last section. Yeah.
You were saying it's confusing, nice. This, like, high school, the reason I need to get.
Yeah. They are equivalent. And one thing you could do, right? So if we look at this passive transformation, I'm saying this on the fly, so I'm a little nervous that I might say something dumb or just wrong. But notice what's happening here. So I've got x on the right, x on the left, and that's a transformed x. Now, if I define the transformed x as my x prime, this is equivalent to saying that this f prime of x prime is f of t inverse on x, which is exactly what we had up above. And the claim being that active and passive transformations are the same. I go back and forth upon whether I find it easier / better to think about it as an active transformation or passive transformation. It gets especially hairy when you look at derivatives, because I can ask, what is the derivative of f with respect to x? And I could ask, what is the derivative of f prime with respect to x, and how are those derivatives related? And then I could compare the derivative of f with respect to x and derivative of f prime with respect to x prime and all the various combinations. There is a part of me that's tempted to have you think about that in the homework. There's part of me that is not tempted to have you think about that. We'll see again where we'll see what happens on Monday. All right, good. Other questions? The question about the derivatives, I would say, is less important in the context of this course. It's really valuable in the context of generally field theory, right? You want to ensure that your evolution equations are invariant under Lorentz transformations, or really Poincare transformations. And so you want to understand how derivatives transform to ensure that those evolution equations are the same in different coordinate systems. So in that sense, in that context is very valuable. I don't know at the moment offhand context in which thinking about derivatives and active and passive transformations is that useful in this course. So that would be I think it's important, but I think it's not so important in the context of this class. Good. Other questions? Great. And I recognize that not everybody in this class is going to go on to field theory. Okay, great. We've got about 5 minutes. What do I want to get to? So I don't know that I'll be able to formally get to what I want to get to a good stopping point in the next 5-ish minutes. So let me just give you a sense of the bigger picture, which is thinking about time evolution of quantum states in the active and the passive pictures, that I can think about applying that time evolution operator to the state psi, and I'm actively pushing that state forward in time. But if I think about, say, what is the wave function, I'm hitting my state psi with an x broad, then my psi of t is my x time evolution operator psi. And as I said, I could think about the u acting to the right. That's the active transformation. I could also think about the u acting to the left. And that would be the equivalent passive transformation. And so what would it mean that I now have my eigenkets depending on time? The eigenkets are the eigenvectors of operators. So my eigenkets depend on time. Well, now the way I should think about it is rather that my operators depend on time. So I can think about the change of basis being effected on the operators. So I'm going to have what's known as a Schrödinger picture of time evolution, where I think about an active transformation on the state itself, leaving the operators untouched and the basis states untouched. Or I could think about the Heisenberg picture, where rather I think about the change of basis in quantum mechanics, which is the change in coordinates that we've been talking about here, and is a passive transformation while leaving the state unchanged in time. So that's the bigger picture. Let me pause there if there are any questions on that bigger picture. Yeah. I agree with your last statement, right? So it's not that we're assuming that there's no time evolution of the KET. We are explicitly saying we are not applying time evolution to the KET. We're rather applying a time evolution to the operators. And then perhaps just to sketch things, so the Schrödinger picture, we're going to say that psi as a function of time in the Schrödinger picture is the time evolution operator of the initial state in the Schrödinger picture. And then my various operators, my x of t, my momentum of t, so on and so forth in the Schrödinger picture, these are equal to x of the Schrödinger picture at the initial time, p in the Schrödinger picture at the initial time. I think you know what I mean by equals on my comments. All right. And then I contrast that. I'll have a nice summary here. Where is my nice summary? Here is the Heisenberg picture, where I say that my psi as a function of t in the Heisenberg picture is equal to my psi t0 in the Heisenberg picture. And I say my, x operator in the Heisenberg picture, this is the similarity transform i.e. a change of basis from the operator at initial time, giving me the operator at final time. And I require that when there's been no time evolution, the two pictures coincide. It's called operator, general operator in the Heisenberg picture at time t0, general operator in the Schrödinger picture at time t0. Absolutely, great. That's an excellent point. So the probabilities can't depend on the picture, and the expectation values cannot depend on the picture. Yeah, I'm past torturing you. That was the projective representation part. Yes, this is, I would say, exceptionally valuable for 3 reasons. I'm in no particular order. I've not thought about the order of the reasons, but reason number 1, it's basically always valuable to have a different way to compute the same thing, because one way might be easier than another. Number 2, we're going to see a beautiful and deep connection between quantum mechanics and classical mechanics, because with the Heisenberg picture, one has the Heisenberg equations of motion. The Heisenberg equations of motion tell me that the time evolution of an operator is equal to I commutator operator with the Hamiltonian. Unless there's some additional explicit time dependence. And what does that look like to you? Yeah. Yeah, so this is exactly the connection with classical mechanics, right? And it has to be the case. I have to be able to take h bar goes to 0 and get classical mechanics. We see exactly it right here. The final reason is that the way to have tractable time-dependent perturbation theory to, for example, compute the decay time of the first excited state of hydrogen, which you will do with Molande to leading order and get the right answer to within 1%. You use what's known as the interaction picture, which is an intermediate picture between Schrödinger picture and the Heisenberg picture, such that you can, in a controlled way, break up the perturbation in a way that you can then calculate things in a perturbable series. So offhand, those are the three reasons why I'm introducing you to the Heisenberg picture. Yeah.
You briefly mentioned these topics.
Yeah. Yes. Yeah. Good. Cool. I propose we wrap it up. Have an amazing weekend.